Now, we will learn some essential calculations needed to verify the mechanical design of the sample probe. We will confirm that the probe will not fail due to the different forces exerted on it while it is inserted in the path of the process flow. Let's begin. First, we need to understand these facts. When a fluid flows around a blunt object in its path, vortices are formed downstream of the object. This is commonly referred to with many names. A wake or vortex shedding, von Karman vortex street, or flow vortices. A wake frequency calculation is used to determine or prove the required dimensions and suitability of a sample probe based on the process conditions. The wake has a specific frequency, which is a function of the diameter of the sample probe and the fluid velocity. If the wake frequency coincides with the natural frequency of the probe will vibrate, and it leads to its destruction. We should calculate the harmonic frequency of the probe and calculate the induced frequency from the vortices. The standard then requires a safety margin to be applied such that the induced frequency or shed frequency is no more than 80% of the probe harmonic frequency. Also, calculation of bending stress should be done to confirm that the probe will not fail due to bending stress. The bending stress should be below the yield stress of the probe. Now let's check together real examples for wake frequency calculations and sample probe stress calculations, done in an ethylene plant on two different probes. First, let us understand what data we need to start the calculations. They are mainly two sets of data: the process details and the probe details. Process details are the process media, maximum flow rate and line velocity, fluid density and line pressure and temperature conditions, the process pipe inner and outer diameter. And finally, the virtual mass factor, which is a dimensionless factor related to fluid mechanics. It equates to 1 in case the fluid is in a gas phase and 0.9 in case of liquid phase. Second set of data are the probe details such as inner and outer diameter, insert length, exposed length, probe material density. Modulus of elasticity, which is a quantity that measures the resistance of the probe material to being deformed non-permanently when a stress is applied to it. In our case, and for stainless steel 316, the modulus of elasticity is 1.96 times 10 to the power 6 kilograms force per centimeter square. The modulus of elasticity of an object is defined as the slope of its stress-strain curve in the elastic deformation region. Yield strength indicates the limit of elastic behavior and the beginning of plastic behavior of the probe material. Prior to the yield point, a material will deform elastically and will return to its original shape when the applied stress is removed. Once the yield point is passed, some fraction of the deformation will be permanent and non-reversible and is known as plastic deformation. In case of stainless steel 316, the value is 207 Newton per millimeter square. The Strouhal number or constant is a dimensionless number describing the oscillating flow mechanisms. We see in this graphs the Strouhal number SR as a function of the Reynolds number, R, for a long circular cylinder. The value of the Strouhal number is approximately 0.2 along wide range of Reynolds number. So we will use value 0.2 in our calculations. For those of you who don't know what is the Reynolds number, it's a value that helps predict flow patterns in different fluid flow situations. At low Reynolds numbers, flows tend to be dominated by laminar, sheet-like flow, while at high Reynolds numbers flows tend to be turbulent. We will have more details about this number and how to calculate it later on during this course. In fluid dynamics, the drag coefficient is a dimensionless quantity that is used to quantify the drag or resistance of an object in a fluid environment, such as air or water. Lower drag coefficient indicates the object will have less aerodynamic or hydrodynamic drag. It depends greatly of the shape of the object and the path of the flow and on the Reynolds number. From the shown graph we will use 1.5 in our calculations. Now and after we understood every parameter that we will use as an input to our calculation, we will start calculating the natural frequency of the sample probe that depend mainly on the probe specification. Natural frequency, as we see from this equation, is a function of the Fm, which is the virtual mass factor, also is function of L, which is the insert length, and it is also function of the inner and outer diameter of the probe and its modulus of elasticity and probe material density. Shed frequency or the vortex frequency equals to Strouhal constant multiplied by the line velocity over the probe outside diameter in meters. And in our example and after calculation we find that the shed frequency calculated is 53% of the natural frequency. This indicates that the probe is not subjected to resonance at its natural frequency, and will not fail. To confirm that the probe will not fail due to bending stress, we need to calculate the bending stress that result from the drag force on the probe. We need to make sure that it is well below the yield stress point of the probe material, which is equal to 207 Newton per millimeter squared for stainless steel 316. To calculate the bending stress, first, we need to calculate the pressure difference that the fluid creates across the probe. The pressure difference is equal to half the drag coefficient multiplied by the fluid density multiplied by the line velocity squared. Second, we use this value to calculate the bending moment. The bending moment is equal to the multiplication of the calculated pressure difference, the exposed length, the outside diameter and the insert length minus half the exposed length. Then, we calculate the section modulus for a hollow cylinder. The section modulus is equal to a constant multiplied by the outside diameter to the power 4 minus the inside diameter to the power 4 all over the outside diameter. Next, we divide the bending moment over the section modulus to calculate the bending stress. It should be below the yield stress of the probe material. In this example and after the calculations we find that the bending moment is 1.49 Newton per millimeter squared, which is very low with respect to the yield stress of the probe material, which is equal to 207 Newton per millimeter squared for stainless steel 316. This means that the probe will not fail due to bending moment. Here is another example with another sample probe. When we calculated the shed frequency and natural frequency, we found that the shed frequency is larger than the natural frequency, so the sample probe may be subjected to resonance and it will fail. So, the solution that the designer used here is to weld a velocity collar to the sample probe. But, is there other solution to fix this problem? The answer is yes. Let us check the remedies using structural changes, when the permissible frequency ratio is exceeded. First and most recommended method is shortening the insertion length. It is the most effective method for the improvement of the frequency ratio. Second method is increasing the root diameter. By increasing the root diameter, the natural frequency is increased, optimizing the frequency ratio. Another method of shortening the probe length is to weld a support collar in the nozzle projection length. The nozzle projection length is defined as the length from process pipe or tube outside diameter to height of the flange facing. In this figure, dimension C is the nozzle projection length. The first support collar location will be the nozzle projection length minus 1 inch. Example. For a 5-inch nozzle projection, the first support collar will be at 4 inches from flange face. If the first support collar location is less than 5 inches from the flange face, only one support collar is required. If the first support collar location is 5 inch or more, a second support collar is required and located at first support collar location divided by 2. Example number 1, 1 support collar. If the nozzle length is 4.5, support collar number 1 will be located at 4.5-1, which is at 3.5 inches from the flange face. Since 3.5 is smaller than 5 inches, 1 support collar will be required. Example number 2, 2 support collars. If the nozzle length is 14, support collar 1 is located at 14-1, which is at 13. Since 13 is greater than 5, 2 support collars will be required. Therefore 13 divided by 2 is 6.5 inches. So the support collar number 2 will be located at 6.5 inch from flange face. The standard states that collars are not recommended as a rigid support for the purposes of shortening the unsupported length. This is because probe tip displacements are generally very small, less than 0.5 millimeters. So, any gap between the collar and the standoff pipe inner diameter will render the collar ineffective at reducing the effective unsupported length. Also, like a hammer repeatedly striking a metal surface, the probe will continue to deform, and the gap will widen until there is no contact whatsoever. This could create stress risers in the probe due to the indentations, or it could eventually break welds that may be located near the collar. The collar must be an interference fit to be effective. Another better solution is the use of the screw-on well design. This design reduces the amplitude of oscillation by more than 90% compared to conventional probe designs. The design allows an easy and fast installation of the sample probe without expensive and time-consuming rework on site. With this note, we have concluded our discussion about the design of the sample probe and the importance of using it when extracting a sample for analysis. We have learned when to use or not to use the sample probe. We also have learned how to choose the position of the sampling nozzle on the process flow diagram and on the mechanical drawings. We learned how to select the orientation of the sample nozzle. We also learned the different types of sample probes. Finally, we learned all the calculations needed to confirm the correct mechanical design of the probe and make sure that it will not be damaged due to resonance or bending forces when inserted in the process stream.